How's it going today? How are you doing, Adam?
It's going good.
Hey there, Deb.
Hey.
Hey, Elsie. Okay, Nilla, nice of you guys to show up. Well, all right, so let me let other folks arrive. Miriam, you're not out in public today.
Yeah, I'm just in my dorm room, but even in here, it's so cold and I'm so unprepared that I'm wearing a jacket.
Oh, no.
Yeah, I'm from California, so I basically live in fear of
I
it.
see. All right, hey, Michael, looks like you're cold too.
Yeah.
All right. Okay, two more. Hi, Sebastian. Okay, so I think probably everyone's here who would like to be here. And all right. So this is an unusual lecture. You're all very kind to come. I'm teaching a multivariable calculus class, and these Cornell students have volunteered to help me present a calculation that I felt was too time-consuming to show in the ordinary lecture. So it's outside the normal curriculum, but I think it's so interesting and historically important that I couldn't resist telling this story. And so I hope other people who are watching, any of you out there, might also find it interesting. It's the story of a triple integral that Isaac Newton had to calculate in the course of his work for the Principia when he wanted to show how the planets move around the sun. He wanted to use his newly developed calculus to show that he could explain Kepler's laws, elliptical orbits of the planets, equal areas and equal times, these various laws that Kepler had derived or at least observed. And so one of the aspects that was difficult for Newton is that he knew that the sun was not a point. The sun is an enormous ball of hot gas, approximately a sphere. And so Newton set himself the question of calculating the gravitational attraction of a solid or gaseous sphere on a point particle, which you could think of as the Earth. And he derived this amazing result that even though there's every atom in the sun pulling on every atom in the Earth, and the sun is very big, and all those atoms are at different distances from the Earth, the ones in the sun. Some at the back of the sun are farther away, those in the front of the sun are closer, some are off to the side at different angles. Newton calculated the gravitational pull of all the different particles in the sun, added them up, and showed that the net gravitational attraction of the sun was exactly as if all of its mass were concentrated at the perfect geometrical center of the sun, which meant that he could then replace this enormous ball with a single point at the center, for which his law of universal gravitation was much easier to then analyze for the motion of the Earth. So this is, I think, probably the most important triple integral of all time. And since we're calculating triple integrals right now in our course, I thought this was a juicy example for us to look at. I should say, for the sake of honesty, that the way we're going to do it is not exactly the way Newton did it. At the end, I'll show you his argument, which I'm not going to go into it in detail. I just want to show you some pages from a book I found where, if you want, you can read it. But Newton uses geometry, a kind of hybrid of geometry and calculus that is not the way we do things today, and that you would probably find a little bit tricky to read. But it's fascinating how much he could do with pure geometric arguments, supplemented by thinking about infinity and limits and that kind of thing. Okay, but let's do it the way we would do it. And so let me share my screen here. There are a lot of steps in this. It's going to take us probably, I don't know, close to an hour. So you're good sports for coming out today. Let's see. All right, so share my screen. And please feel free to ask questions if at any point I'm going too fast or making a mess. I might also make mistakes, so be sure to catch any of those if I do. All right, here we go. All right, so Newton's triple integral here. Let us restate the problem. Oh, I'm going to get off this background. Don't need that or this. Okay, so again, as I say, we're going to consider a spherical ball of, to keep it simple, of uniform density. Or it actually, we won't need that. If the density just depended on the distance from the center of the sphere, that would be enough. That is, we can add up the contributions of all the atoms, one spherical shell by another, starting at the center and then expanding out till we get to the outer radius of the sun. And so as long as the density only depends on the radius and not on the angle, either theta or phi in spherical coordinates, the calculation we'll do will work. But for simplicity, let's suppose it's just a uniform density sun. What we want to show then, as I say, is that its gravitational pull on a point mass outside of itself is the same as if all of its mass were concentrated at the center. So we're going to be assuming Newton's inverse square law, which you must have learned in your elementary physics classes, that the force due to a mass m on another mass, capital M, or the other way around. Actually, I'll think of capital M as the mass of the sun. That looks big. This is the mass of the Earth. That looks small. But anyway, if they're separated by a distance r, as here, and we think of them both as point particles, then the force is this Newton's gravitational constant times the mass of the first times the mass of the second. And then the key part, this inverse square dependence on the distance between them. Okay, so we're going to assume that for every pair of points. Now, I just want to say that this idea that you can replace all the mass by putting it at the geometrical center of the configuration of all the little masses, in the case of the sun, at the center of the sphere, that's not an obvious property of center of mass. We talked about center of mass the other day in lecture, and you might think, well, of course, where else could the force act from if not the center? But that's just wrong intuition. Here's a little example. Think about two masses. Let's suppose they're all just unit masses for simplicity, mass 1. And imagine I have these two little specks of the sun, just 2 points, at a distance 1 and 3 away from some point at the origin. So we could ask, what's the net gravitational force of these points at distance 1 and 3? Is that the same as if both of them were concentrated right here at halfway in between at the center at 2? And you'll see it doesn't work, because the force of these two particles of mass 1, ignoring the g, and we're treating masses as 1, basically the force would be 1 over 1 squared plus 1 over 3 squared from this configuration, which if you add it up is going to, it's really proportional to, not equal to. But if you add that up, you get 1 plus 1/9, or 10/9. Whereas if we concentrated both of these particles at the center, and now we have double the mass there, they would exert a net force of 2 over the distance squared, which is now 2. So 2 over 2 squared, that's a half. And that is definitely not the same as 1/9, right? It doesn't work. Concentrating the mass at the center isn't the same, doesn't give you the same result. In fact, you can see that it's, which case is larger, which gives the stronger pull? This case gives the stronger pull. And that's because this one is so close. This really dominates. So anyway, the point being that it's not just a simple property of taking the center. Somehow, this statement of Newton's must depend on the geometry of a sphere. That's got to come into it in some way. It doesn't work for collinear points. Did you want to ask anything about that? Does that make sense? We could think of other cases. Obviously it's very abstracted to just do 2 points, but it just shows it's not a matter of the sphere, the center of the arrangement of points. Okay, so let's now move on to thinking about spheres. And for that, of course, we're going to want to use spherical coordinates, which we just introduced the other day. So I just want to remind you that, there's our usual picture of the coordinate system, with phi being the angle coming down from the z-axis. The old distance from the z-axis that we use in cylindrical coordinates, that's what we call r, and it's related to this distance, rho, the distance from the center in spherical coordinates by drawing this little triangle here and then reading off r is rho sine phi. And, you know, if we want, we can write down what x, y, and z are in spherical coordinates by this, looking at these triangles. We're not going to really need that so much as the volume element that we talked about in the last lecture. When we sweep out a little volume, we imagine sort of moving in an infinitesimal amount away from this point, either in the phi direction like this, or we could extend out in the radial direction along rho, or we could also sort of sweep around sideways this way by sweeping the angle theta around the z-axis. That traces out this little, you know, approximately it's a box. It looks sort of like a rectangular box with sides that would be rd theta in length in this direction, d rho as we go along the radius, and rho d phi along this way, coming down. Anyway, when you multiply those three together, you get the volume of this little infinitesimal box, which is this formula for our volume element dV. Okay, so we mentioned that last time, and we're going to need that because we're going to think of each point in the sun as not just a single point, but as an amount of mass contained in this little box. And then we're going to add up over all the boxes, each of which is gravitationally pulling on this test mass far away. So when we do our integration, we're going to need that dV. All right, so now I'm ready to dive into the guts of the calculation. And at this point, I haven't pre-written anything, so like, other than this diagram, so we're going to just start writing. Okay, so here's the setup. I've got this big sphere, which is supposed to be our solid ball, that's pulling on a mass up here at a distance, capital R, away from the center of the sphere. And what's gravitationally attracting this little mass is bits of mass in the sun. Here's a typical one that I'm going to think of as an infinitesimal mass element, dm. That's sort of what I keep calling an atom. And so that atom is then pulling on this mass, pulling it towards the sun at a distance b, where the b will change depending on which mass element I'm thinking about. So I'm going to look at this, you know, some typical one here, dm, and it's convenient to think about all the masses that are sort of equivalent to that in the sense that they could be all around this little ring here, right? I mean, by symmetry, they're all at the same distance, b, away from that mass up here, m. And we want to calculate the net effect from that ring. And then I'm going to do that over all the rings possible. I could sort of calculate the full force from a spherical shell. Also, I don't have to just do it here on the outer surface of the sun. I can think of this rho being any point, you know, sort of inside touching any point inside the solid ball anyway. So this is just sort of one example of the forces being exerted. All right, so let's start writing down some trigonometry at this point. Let's see, so this little dm exerts a force, dF, an infinitesimal force on that mass, little m, which by the inverse square law would be g times that m times the dm that's pulling on it, divided by the distance it is away, so in squared, b squared. Incidentally, when we're adding up all the forces coming from the sphere, will you agree with me that the only force I need to think about is the force along the line connecting this to the center? Like, there's not going to be any sideways force on this mass. Biaxial symmetry, right? Any force this way is going to be canceled out by a force that way. In other words, like, the stuff on this side of the sun is exactly counterbalanced by the stuff on that side of the sun. So there won't be any net force in the x or y direction. It's only going to be in the z direction. Okay, hope that's clear. So I'll just make that little remark that by symmetry, we only need to think about what's happening in the z direction. We're going to have f in the x direction is 0 and f in the y direction is also 0. Okay, so all we really need to think about is the z component of the force. And so let's figure out what that is. So let's in particular think about the z component of this little infinitesimal bit of force that I'm looking at so far. It's going to be gm times this little mass element dm over b squared. But then I have to include, since I'm only interested in the z component, I'm going to get cosine of alpha, where cosine of alpha refers to this angle. This is the alpha right here. It's going to be the angle measured from the mass down to my mass element, right? This angle alpha is important. Now, why am I saying cosine of alpha? How do I know that's the right component in this direction? So, I don't know. Is it clear from the picture? That is, if I think of this kind of picture, you know, if I have this df acting in that direction, if I want the vertical component, I'm going to want to take df times cosine of alpha. Right, I mean, think of it as if it were a triangle. The amazing thing with forces is that they act as if they were lengths, although they're not, but they obey the same trigonometry. So the vector component of that df in this direction will be df cosine of alpha. So that's the right, is that clear? I don't know. Did that take a second to get? Right, just resolving the force law.
Yeah, it's clear.
Yeah, you're okay, Michael, with that? All right, good. So we got that. Now, geometrically, we should figure out what cosine of alpha is. And we can do that by drawing another triangle, which is this one right here. This triangle. Look at this, this, and this. Okay, I'm going to read off cosine of alpha by drawing this picture. So let's go like that, and then say like this, where this distance is rho. So let me make this a little bigger. That's rho. This is what we're calling phi. Up here we said this is alpha. This distance is what we were calling b. And now I want to draw this little dotted line to make a right triangle in there. The reason for doing that, well, first of all, let's read off some stuff. I mean, from the law of cosines, we can get a relation between some of these quantities. The one we were interested in, I mean, if you look at this b squared that appears in the denominator, that's of interest. And the law of cosines applied to this triangle tells us that b squared will be, remember, this distance is r. That's the distance from the center of the Earth out to the little, or center of the sun out to this mass. So we'll have b squared is, okay, how does it go? It's r squared plus rho squared minus 2r rho, cosine of the angle between them, which is phi. Where I'm looking at this right here to do my law of cosines on b. So hopefully you remember that from your high school trig class in pre-calculus. And do I need anything else? Yes. I also want to read off cosine of alpha. Remember, I was interested in that. And I can get cosine of alpha by looking at this triangle. So to do that, I need to know this distance right here to that point. So what is that? that distance, let's see, right here, that distance would be r minus whatever this distance is, which I guess I would call that. That's rho cosine of phi. So r minus rho cosine phi is this. And so it looks like cosine of alpha is that distance that I just wrote down divided by the hypotenuse b, right? Where I'm focusing on this triangle right here. What's going on? I mean, what's happening is, maybe you should think of it like this. Why am I doing all this? In this picture, alpha is kind of not a super convenient angle because it depends on which mass point I take. It's actually a little nicer if I can relate everything to this angle, phi, that's related to the center of the sphere. That's going to prove convenient for when we start doing our triple integrals, because we're going to integrate over phi, over theta, and over rho. And so it's handy to have everything in terms of phi. And so that's why I want to replace, I'm going to use this formula to get rid of that cosine of alpha and express it in terms of phi. That's going to be a useful move. And I also can replace this b squared by something else in terms of phi, this. So it's all going to be very handy if we do that. And so let's move on. That was our strategy in dealing with all this geometry here. All right, so let's see what I get if I do all that stuff. It looks like my df in terms of all this, df in the z direction is, let me scroll back. So I have to write g little m. Now, what's the dm? I'm trying to copy this formula right here. Maybe I'll just replace everything we've done so far and I'll deal with dm in a second. So I have gm over b squared cosine alpha, and then d, this big M, which I'll deal with shortly. But so this is gm. Let's whip out the law of cosines here. So I get r squared plus rho squared minus 2 r rho cosine phi. That was b squared, so that's now in the denominator. The cosine of alpha we just dealt with. We said that was going to give us r minus rho cosine phi all over b. That's interesting. Actually, I'm seeing b again. This was b squared right there. So I'm actually getting b cubed in the denominator. So that's interesting. Maybe I'll just write this b. Let me replace that b by, well, okay, I'm going to replace that b by the square root of this same expression that's in the law of cosines. R squared plus rho squared minus 2 r rho cosine phi. So that was replacing cosine of alpha. And then finally, I have to write in dm. But dm, I mean, remember I said that for simplicity, let's think of the case of a homogeneous sphere, uniform density. So that means that the mass is going to be whatever the density is times the volume of that little piece of, like we're thinking of an infinitesimal blob of mass. So it's going to be delta times the volume of that mass, where the dv is our little volume element in spherical coordinates. In other words, right, I've got a tiny volume dv. It has density delta, that's mass per unit volume. So multiplying those gives me the mass of that little blob of atoms that I was thinking about back here in this picture. Those little atoms right there. So I think I've got everything I need now. I've got that the little infinitesimal force produced by that blob, or that little volume element, is gm, that's some constants, r minus rho cosine phi. Got this big denominator that's my b cubed. It's r squared plus rho squared, not minus. That's, sorry, not plus, that's a minus. Two r rho cosine of phi, that's now to the 3/2 power, right? Because it's a square root times this thing. So that's 3/2 worth of that term. And finally, dm, we decided, is our density delta. And then dv, we have to remember, this is where we get to deploy spherical coordinates, that formula for the volume element. So it's rho squared sine phi d phi d rho d theta. Still with me?
Professor Strogatz, I have a quick question.
Sure, please.
So you said that for this problem, it doesn't actually matter whether the sphere is of uniform density or if like delta would be like k rho.
Good, yes, it could be, no, I didn't mean that it was k rho. I meant that the density only depends on radius. It could be some arbitrary function of rho.
Okay, but that won't affect the triple integral that we do?
It would change the triple integral, but basically the way we should think of it is, if we can prove the result for a spherical shell, something that's all at the same distance rho away, if we can prove this, that the property we want, that all the force acts as if it were concentrated at the center, if that's true for any spherical shell, then it will be true for a whole volume filled with spherical shells. They'll all be acting as if they were at the center.
Even if each of those individual spherical shells has a different density?
Right.
Okay.
If you prove it for each spherical, because any given spherical shell has a constant density, because that density only depends on rho, and all those points are at the same rho.
Right. And all of those shells would have the same or center.
Right, that's the point. They all have the
Okay.
same center. They're concentric shells.
Okay, that makes sense. Thank
Right.
you.
So it suffices to prove it for a shell. And actually that's what Newton did. So Newton in his geometric argument did do it for one shell at a time, and then he did it for a whole solid ball filled with shells. Okay. We're not going to need to do it that way because I'm trying to make life easier by just assuming constant density, but we could do it. We could do what you said, and that's actually what Newton did.
Okay, that's very interesting.
That's kind of relevant because in fact, it may not be true that the center of the sun has the same density as the gas out at the edge of the sun. Right? I mean, we probably think that there's a core of the sun that's got nuclear fusion going on, and I don't know. In any case, the result is true more generally. It just depends on, but anyway, let's do it for this simple case. So where are we? We've just derived this complicated expression for the amount of force produced by this little volume element, this little mass element. And now what we have to do is calculus, which is we have to add up all of those contributions of force over the entire solid sphere. And so that's the triple integral. Okay, so now we got to start doing some integrals. Fortunately, a sphere has nice limits of integration. really nice. And so the calculation that we want to do is the net force in the z direction is the triple integral of all these infinitesimal forces taken over the whole ball, the whole solid sphere. But what that boils down to when we write everything in spherical coordinates now is that that will be, well, what's the region of integration? So think about the phi. I mean, it's extending over the whole, or we can do them in any order actually, because they're all going to be constants. Theta goes from 0 to 2 pi, swivels us all the way around the axis, the symmetry axis. The phi extends over the whole of the sun. So from the North Pole down to the South Pole. And the radius, the rho, the radius in spherical coordinates, goes all the way from the center of the sun out to the outermost edge. So let's think of it as being radius A. And then we just have to integrate our integrand, which I can copy down now. So there's a big fraction here. I have, let's put the constants out first. G, M, and delta, those are all constants. Then there's stuff that depends on phi and rho, like rho squared, sine phi. Oh, let's actually notice there's some more stuff before I start writing D. I also have that factor of r minus rho cosine phi. And that, gee, I didn't even make my denominator, my fraction bar big enough. Am I running off the page? No, I think I'm okay now. Right, then I have d rho d phi d theta. I haven't missed anything, right? That's everything in the numerator. Yeah, and then I have this messy 3/2 power stuff. R squared plus rho squared minus 2r rho cosine phi to the 3/2. Okay, so looks intimidating, but just stare at that for a minute. As in a lot of these problems with axial symmetry, nothing is happening in the theta direction. You'll notice nothing in the integrand depends on theta. So we can instantly do the theta integral. It will just give us 2 pi. Right? I mean, everything else is independent of theta. So we could do that first, and we'll just get 2 pi times then a double integral. Actually, while we're at it, why don't we pull out the other constants? So 2 pi gm delta. Okay, and then some honest to God integration. So go from phi equals 0 up to pi, and rho equals 0 out to a. And then rho squared r minus rho cosine phi sine phi. So I'm putting down all the stuff that depends on phi while I'm thinking of it. And d rho d phi. And then the big denominator, r squared plus rho squared minus 2r rho cosine phi to the 3/2. Okay, so what to do? You can see, I mean, it's not obvious whether we should do the phi integral or the rho integral first. They're both kind of complicated, aren't they? Because if I wanted to do the rho integral first, got rho squared, there's a rho, but then there's rho appearing down here and also in here. But it's kind of mixed in with the phi stuff through this term. It actually turns out to be a little more convenient to do the phi integral next. At least that's the way I've done it. So let's try to do it that way. So let's do the phi integral first. We can do them in either order because the limits of integration are constants. So there's really no difficulty. I mean, no issue with which order we do it. Let's do the phi integral first. And remember, when we're doing that, we have to think of holding rho constant. And realize that what that means physically, if you're holding rho constant, you're now living on a spherical shell. Right? Points at constant rho are points at a constant distance from the center. That's a spherical shell. So doing the phi integral first means we're basically calculating the force contributed by a spherical shell. So echoing Newton's approach. Holding rho constant. Okay, so I find it helpful to introduce a little notation here. Rather than keep writing all these constants over and over again, let me just pick out the stuff that depends on phi. So if I focus on that, where are some phi terms? The only phi terms are right here. Right. So I'm going to define that thing that I just circled as I1. I'm going to have a series of integrals I have to do, so I'm going to start numbering them. Let's define. So by the way, this is where you have to be patient. I mean, it's going to get bad, but then it's going to get good. So it's worth it. It's very satisfying. It's drama, right? The hero gets in trouble before the hero gets rescued. So the hero, I don't know who the hero is, but you know what I mean. So let's define I1 to be this integral 0 to pi of sine phi r minus rho cosine phi d phi all over that denominator, r squared plus rho squared minus 2r rho cosine phi to the 3/2. Okay. So can we do this? Well, so what's the principle for doing integrals? I would say good advice is you look at the nastiest thing and call it u. Right? Try to replace the bad stuff with u. That's usually a good substitution. So in the spirit of that, I'm going to let u equal, how about that junk in the denominator? So you could define u to be that 3/2 power, but the way I defined it was to just be the stuff inside the 3/2 power. Cosine phi. Yeah, let's do that. So then du would be, so taking the differential of both sides. Well, keep in mind r is a constant. Rho is being treated as a constant, right? That's what we said. We're holding rho constant. So when I take the differential of rho squared, it's not going to contribute anything. It's being held constant for now inside this other rho integral. So the only thing that has a differential is phi. Phi is the only variable for now. And so this is going to give us, what, minus 2r rho. The derivative of cosine of phi is minus sine phi. And I'm actually taking a differential, so that should say d phi. So putting all this together, cancel out those negative signs. you're getting 2r rho sine phi d phi. Okay, and what else? I guess I should also look at trying to simplify this term up here and express it in terms of the u. Right, I'm trying to convert my integral from a phi integral to a u integral. So I should try to replace everything in terms of u that can be expressed in terms of u. And so in particular, you can observe that, I mean, what I need to replace is this rho cosine phi. So let's see what we can say about that. Well, actually, it's kind of convenient. You can see a rho cosine phi appearing here in the definition of u. So that's pretty good. We can then say that rho cosine phi in terms of u is going to be r squared plus rho squared minus u all over 2r. Right? Just doing a little algebra on the definition of u. Maybe it's worth putting, oh, yes, is there a comment or a question?
2r rho, no?
Ah. Oh, well, no, because I have the rho right here.
Fully. Okay, yes, sorry.
Yeah, right? So I was saying rho cosine. I mean, if I were solving for cosine phi, then you're right. But I'm writing rho cosine phi because that's what I'm going to need. So I just skipped a little step there. Okay, so why was I doing that? Because I want to simplify this term. I want to make that in terms of u. Or no, it's not that one. It's this one. I want to replace this by something in terms of u. So with this in mind, but yeah, I'm glad you're following. So then we get r minus rho cosine phi becomes r minus the thing I just wrote down. So that's, let me break it into some terms. There's, I'm going to first look at, I'm copying down this term, putting it here. And then I'm going to look next at this term and write it down. So I have to go minus rho squared minus u all over 2r. And when I clean that up by putting it all over the 2r, it ends up becoming, well, let's think of it this way. It's 2r squared minus r squared minus rho squared plus u all over 2r, and I can simplify that numerator to just be r squared minus rho squared plus u all over 2r. Okay, so that was just to try to convert everything into u. And so where am I? I'm trying to simplify this first integral, I1. And so what have I accomplished? I've now calculated an expression for this term in terms of u. This term, of course, is going to be very sweet in terms of u. That was the whole reason for the definition of u. And the sine phi d phi is not going to cause us any trouble because that has a very nice expression in terms of the differential of u. So everything's going to be very clean in terms of u. It ends up becoming this. I'll get I1 is integral. I have to write the limits now in terms of u. So my lower limit, which used to be what? My lower limit used to be phi equals 0. if I think about what that is in terms of u, when I put phi equals 0 in here, cosine of 0 is 1. So I'm getting r squared plus rho squared minus 2r rho. You'll recognize that's a perfect square. That's a perfect square of r minus rho all squared. So I'm getting stuff like u equals r minus rho squared up to, it turns out up here we get r plus rho squared. And then the integrand has terms that look like du over 2r rho. So this is my sine phi d phi term from before. Then I have a term that looks like the one I just copied down, that's immediately above. R squared minus rho squared plus u all over 2r, right? That's this thing. And finally, what else do I need? I mean, what have I done? I've just dealt with this term. That's this. I've dealt with the sine phi d phi. That's this. And what's remaining is this denominator, but that's just u to the 3/2 power. So, but it's in the denominator, so I have here a 1 over 3/2. 1 over u to the 3/2. And it's getting a little better because these u integrals are not bad. Notice there's actually 2 of them. So why do I say 2 of them? Because u appears in this expression as u, and then it doesn't appear at all here. So you can basically think of this as kind of like a constant plus u. And then that's being divided by u to the 3/2. And this junk is just constants. Again, rho is regarded as a constant in these integrals because we're on a spherical shell. So if you take out the stuff, I mean, basically this breaks up into 2 integrals. Let me write them both down. One that has a u in it and one that doesn't. So what is this? Taking out constants, like here's some constants here in the denominator. Taking those out, I get 1 over 4 rho r squared. Then integral from r minus rho squared up to r plus rho squared. And then as I said, this term breaks up into 2 different terms depending on whether it has a u in it or not. So let me write them both. One of them is r squared minus rho squared. And that one gets to be over this u to the 3/2. And then there's another term, which is plus a u, right, that u, over a u to the 3/2. So that ends up making a u to the 1/2 power in the denominator, right? You can cancel out u to the 2/2, so to speak. So this gives us overall a, actually, it's nice. It's just u over u to the 3/2, so it's just u to the 1/2. Negative 1/2, like that. And all of that is the stuff in my integrand du. Okay, I did that very slowly and ponderously, but hopefully it's easy enough to follow. Right, so I now have 2 integrals I have to do, which I'm going to think of as I'm dealing with 1 over 4 rho r squared integral from, well, let's just call it this way, or let's just write it this way. I'll say this is a sum of two integrals, I2 plus I3, where I2 will refer to doing this integral and I3 will refer to doing that one. Okay, so can I give you a little foreshadowing of something? I mean, actually, maybe I should have done this earlier. We're going to get some fantastic cancellations. I already mentioned that. But just to foreshadow how this is all going to turn out, it's going to turn out that this I1, which is the thing we're laboring over, remember that this is supposed to be my spherical shell integral, this is going to turn out to equal 2 over r squared, period, independent of rho. So I'm going to show that. That's where we're going. Maybe this will give you a little motivation to keep sticking with it. We're going to show that this equals 2 over r squared. Now notice that's a fantastic thing. The fact that it's independent of rho means this integral is the same for every spherical shell. That's good. That's really good. Every spherical shell is going to contribute this number 2 over r squared. I still have to integrate over rho later, but it's really interesting that this is the angular dependence. Once you integrate out the angular dependence, it's the same for every spherical shell. And that's already giving us a hint that something special is happening at the center, and the rho is not going to really affect anything. The different shells don't behave differently. Okay, so let's see that that's really true. Remember, this integral we're doing here is still just I1. So let's try to crank it out. Okay, we're almost there. I just have 2 integrals. Let's keep trucking. So, all right, let's do I1 first. Oh, sorry, do I2 first. Okay, so what is that? That's just, well, oh, actually, I don't seem to have done them in that order. Oh, yeah, I am doing that order. Okay, so I2. Well, I have to integrate u to the 3/2, negative 3/2 power du. And you can remember what that is. That's negative 2 u to the minus 1/2. But now we have to remember what our limits of integration are. They are r minus rho, here's a u, r minus rho squared, and u equals r plus rho squared. So there's a lot of algebra now. But when I plug that in, I get minus 2. Notice how convenient it is. I'm taking a half power of something squared. So, right, I'm taking a square root of a square. So it's as beautiful as can be. This is giving minus 2 times, when I take the half power of r plus rho squared, I get r plus, it's the negative half power. I get r plus rho to the minus 1. And then the lower limit gives me minus r minus rho to the minus 1. And so now just clean that up. So what is this? This is negative 2 over 1 over r plus rho minus 1 over r minus rho. Put that over a common denominator. Minus 2, so let's see, I get r minus rho minus r plus rho all over r squared minus rho squared. That's just multiplying those two terms in the denominator, in that common denominator. And then the numerator, let's see, the capital R's cancel out, and I'm left with what? Minus 2 times minus 2 rho over r squared minus rho squared. So that's 4 rho r squared minus rho squared. Now, okay, but you may remember, let's look right here. What did I just do? I just calculated just the u to the 3/2 part of this integral. But look at that numerator. It says r squared minus rho squared, which is exactly what we're seeing in this denominator. So those are actually going to cancel out right now. Ho ho. So when I actually do the correct I2 integral, I mean, what is the, right? I have to remember this numerator. So what is this coming down to? The summary is, so r squared minus rho squared over u to the 3/2 du, that integral, you know, by this cancellation of this term with this term, it's going to give that this all equals 4 rho. This is my I2. So that's coming out pretty nice, as Larry David would say. Pretty good. I realize it's a lot to try to follow, but are you with me so far? So I have to do I3. We're coming into the home stretch. So let's do that. What was I3? I3, I have to look at doing u to the negative 1/2. I'm not going to forget this factor in the end. That's coming later, but I just want to deal with my u to the negative 1/2, and I have to think about these limits. Okay, so let's just quickly do that. Okay, next we have to go dealing with I3. All right, so doing the integral of u to the minus 1/2 du, that gives me 2 u to the 1/2, and then that's again supposed to be evaluated for u limits r minus rho squared and r plus rho squared. So this simplifies to 2 r plus rho minus r minus rho, and that just becomes 2 rho. Oh, sorry, 2 rho times 2. So 4 rho. Wow. So that's, all right. So let's see. Now, the way I had defined I3 was just this thing right here. But I have to remember this prefactor that's multiplying my I2 and I3. Okay, so having done those, let's put everything together. Where am I? I've got I1 let's go back and copy stuff. I1 was 1 over 4 rho r squared I2 plus I3, which, unless I've dropped some factors here, is 1 over 4 rho r squared. Now, what did I calculate? My I3, I said, was 4 rho, and my I2 was also 4 rho. So the 4 rows all cancel out, and I'm left with 1 over 2 r squared is I1. Wow, right? It doesn't depend on row. The row's canceled.
Wait, sorry.
Yeah.
Did I do that
you
wrong?
go.
Would it be 2 over r
Oh,
r
yes. Oh,
squared?
sorry. Thank you. Thank you. Good save. Yikes. Good. Getting too carried away because I can tell I'm almost done. Right. 2 over r squared. And that's what I think I advertised earlier, didn't I? Did I say back here? Yeah, I said back here, we're going to show that I1 is 2 over r squared. So we did. Now we're really just about done. So what's going to happen? 2 over r squared. So what's left? Well, I mean, let's scroll back to just see what was left. We said that the integral we have to do is, we were going to do the phi integral first in this expression. But I still at the end have to do something with rho squared d rho times all the stuff that depended on phi. So I've now done the phi integral, right? But what I didn't do was this rho squared d rho times what we just calculated. So now coming down to the end, we are left with Fz, the final thing, the force exerted by the sun on a planet, is, putting in all the constants back again, you'll just trust me, these are the ones I had, 2 pi gm delta. Now we have to integrate over the solid sun, 0 to a. I just calculated I1 to be 2 over r squared. Right, this is going in here. And then I have to do my rho squared d rho, which is still coming along for the ride. Right, that's the point. This thing in the parentheses doesn't depend on rho, so my rho integral is very easy. I just get 2 pi big G m delta 2 over capital R squared. This gives me, doing the rho integral, I get a cubed over 3. I think, right? Because it's rho cubed over 3. So, oh, and then let's put all this together. Wow, let's see. I see 4 pi a cubed over 3. That's a very suspicious thing. Times g m over r squared. Maybe the delta belongs here. So you see it now, right? 4 pi a cubed over 3 is the volume of the sphere. Times delta, it's a homogeneous sphere. That is the mass of the sphere. In other words, that's big M. Bingo. That is as if all the mass of the sun were concentrated at the center, just as a point particle. So how about it? I love it. Good, and it worked. So thank you for the help. That's the triple integral that you can see I didn't want to do in class because I already get in trouble for going overtime in class, but we were way over time. Okay, so that's the fantastic triple integral that I couldn't resist showing you. But as I mentioned, Isaac Newton himself didn't quite do it that way. If you want to see how he really did it, I would recommend this book by Niccolo Guicciardini called Reading the Principia. It's a scholarly history of math book by one of the great Newton historians, and he really looks carefully at what's in the Principia. And I'm just showing you a copy here of the pages from Guicciardini's book. Maybe I'll just expand those a little in case you're watching this on YouTube and you want to read. You know, you could, I suppose, screenshot this or get a copy of Guicciardini's book. But anyway, he goes into this argument that I'm not going to do here, except to say, you know, it's kind of fun to read Newton's own language. In the Principia, Newton writes, he says, Proposition 71. He says, I say that a corpuscle, okay, a corpuscle is a little mass, a little test mass. I say that a corpuscle placed outside the spherical surface is attracted to the center of the sphere by a force inversely proportional to the square of its distance from that same center. In other words, a spherical shell attracts a test mass as if all the mass were at the center of that spherical shell. So that's what he means by a spherical surface, a spherical shell. And then he later analyzes, you know, a whole solid body. But it's interesting when you look at his argument with the spherical shell, he just does it by a picture that looks very similar to what we were doing, except he's doing it kind of with classical geometry, and he has all these letters, you know, and he tries to analyze an infinitesimal sliver. So he is doing calculus. He actually thinks about infinitesimals. But anyway, there's this really clever geometric argument. I'll just let you look through it. I mean, he can deduce it. I mean, as Guicciardini points out, the ratio of attractions of two infinitesimal annular surfaces is in the ratio of blah, blah, blah. It's a really fantastic geometric argument. But in a way, it's a lot easier than this triple integral that we did, but you have to be a genius to follow it. But it's there. I mean, it's really all there. So anyway, take a look at that if you're interested in the historical truth of how it was really done. Okay, I've kept you long enough. Thanks a lot, everybody.
Thank you so much, Professor.
Yeah, thank you, Miriam. Thanks,
Thank
everybody.
you, Professor.
Thank
Have a
you.
good day.
Thank you.
Thanks, guys. And see you in class on Monday. All right, bye.
Yeah. Bye.